says the value of Kc is 931.7, and I had some calculations being done here that I forgot to round, but this is exactly from an Excel spreadsheet. That's how these get into Blackboard. But anyway, so we'll work with it. Kc is this number at 572 degrees Celsius for the following reaction: 2 moles of I gas in equilibrium with 1 mole of I2 gas. And now the question is, what is the value for Kp? And so Kc, I'll just write them out again, is going to be concentration of our product divided by concentration of our reactant raised to the second power. And Kp is the same thing except with partial pressures. Partial pressure of our product divided by partial pressure of our reactant squared. So, and just to be hopefully clear, this 2 is this 2. And you might remember that when we were talking about kinetics, we said that in the reaction rate law, coefficients were not necessarily exponents in the rate law. In equilibrium constant expressions, coefficients always show up. And so I see why there's a bit of confusion about this. So, but I don't have a good answer for you other than equilibrium constants always have coefficients as exponents. And for integrated rate, for rate laws, reaction rate laws, kinetics, you always have to do a problem to solve for what are the exponents. So maybe that's the way to think of it. Well, in the lecture outline notes, what I showed you is that for any gas, let's say I2, we can write out the ideal gas law. And if we move the volume over here and put it specifically under the moles, this is going to be moles per liter, which is the concentration in molarity. And so I will cross out my V's. I will put, I'll actually put it up here because I'm going to need to do some work down here. The partial pressure of iodine, I2, is concentration of iodine times RT. And we can plug that into this expression right here for P, partial pressure of iodine, I2. We can now write concentration of iodine, I2, times RT. And we can do a similar thing except for atomic iodine, concentration of I, RT, that's the expression, and then we have to square the whole thing, like so. And then simplifying things, we get that this I2 over I squared times RT over RT squared. One of the RT's cancels out, so we get 1 over RT. And this thing right here is just Kc, and we're left with Kp equals Kc times 1 over RT. And the fact that we know Kc and we know R and T, well, we have our temperature right here, will allow us to solve for Kp. And the general expression that we derived is that Kp equals Kc times, got a little ahead of myself, RT to the delta N, where delta N was the moles of gas of product minus moles of gas reactant. Let's just say moles of gas for products minus moles of gas for reactants. And in this particular problem, we have 1 mole of gas for the product, so 1 minus 2 moles of gas for the reactants. So delta N is minus 1, which means we have a power of RT in the denominator. So now let me go ahead and plug in. So Kp equals Kc, which is, I'm just going to use 931 point, or I'm going to use 932 times 1 over RT. R here, since we're talking about the ideal gas law, is the 0.08206. Liter atmospheres per mole Kelvin. Oop, I sort of ran out of space, but I'm going to try and squinch it in here. And now I have to put in my temperature, not in degrees Celsius, but in Kelvin. So 572 plus 273, or 273.15. Well, I'm going to use 845 Kelvin. So this part here is how I calculate Kp. It's going to equal 932 divided by these two numbers, divided by 0.08206, divided by 845. I get 13.4. as my Kp value, which we would then enter in to solve this problem. Now, maybe this is a good time to talk about the fact that even though these are concentrations and these are partial pressures, my Kc and my Kp values have no units. And I think I briefly touched on this in the lecture outline. First off, they have no units. Second off, that is frustrating to me because I love units. I heart units. And third off, a more advanced study of chemistry is needed to explain what happens to the units. The units basically, there's no easy way to say this. There's a system for canceling out the units when we talk about the relationship between these concentrations and standard state. I guess that's the shortest way to say it. Same thing for partial pressures here. And I'll leave well enough alone before getting even more complicated.